but I was at a museum a long time ago, and I saw a ticket for a Ford Trimotor, and a cross-country ticket on that airplane was $300.
What is that inflation adjusted?
Much
$1
more than
million.
$300. I was like, yeah, it's like the same thing.
The math checks out.
Without inflation. Well, cross-country is more expensive right now, but...
All right, cool. Well, flight sciences. So this is going to be a fun one. This is something that I have a lot of opinions about, but now I spend much less time, but you guys will have all the interesting stuff that we're actually working on. But
as opposed to other things that you usually don't have opinions about.
Fair. That's super fair. All right. So yeah, let's go through intros real quick, and then we'll hop into it. So some of the folks might already know Wes here, but have you kick it off?
Sure. So I'm the head of Darkhorse Engineering, and I'm also currently filling the lead flight sciences engineer role, although soon to be relieved of that, thankfully. And I've been at Hermeus for almost 3 years now, which is pretty crazy. So
one of the OGs. Nice.
Yeah. I'm Tatum. I am an aerospace engineer, I guess is my title. And I've been here...
Very specific.
Yeah, very specific. I've been here full-time since January, but I interned 2 years ago.
So I guess technically that makes you one of the OGs too.
Yeah, I was here when Les was here.
Yeah.
Oh, man. Yeah, I'm James Shields. I'm an aerodynamics engineer and have been working on aeroprop for a while, doing inlet things.
Awesome. Cool. Yeah. Well, I guess the first question that some people might have is, what is flight sciences? So I guess there's probably different flavors of that, but maybe we could each answer it in our own specific version of what is flight sciences. James, you want to start?
Yeah, sure thing. So I usually think about it as like, what doesn't fall nicely into propulsion, avionics, or structures, and kind of throw that out as whatever falls into flight sciences. So that includes all of our aerodynamics, a lot of our performance modeling, thermal aspects of what we're doing, and anything that really dives into those flavor of things is flight sciences.
Yeah. Anything to add?
Yeah. I think it's also more generally if the teams need to talk to each other, they do it kind of through the analysis of flight sciences.
Yeah, it's like the vehicle analysis. So anything that's not like people designing specific hardware is generally what flight sciences owns, and really that kind of like system level integration, like owning vehicle configuration and top level performance and things like that.
How do you see it differently between like systems engineering versus flight sciences, or how much overlap is there really?
Yeah, there's kind of like the aspect of systems engineering that is more like management, where it's like tracking numbers, not really necessarily involved in the design of the aircraft as much, but really just tracking. And I think we could have a little bit more say in the design. So
it's like that one step further.
Yeah, exactly.
Because there's the aspect of performance, and like the configuration really has such a strong impact, especially for like things that are flying this fast. It's like so hard to decouple any of the systems. I think especially in high-speed flight sciences is one of the most critical roles, because it's like you can't just independently design the engine, because the way the inlet shapes the flows that go into the engine is part of the airframe, and like it's almost impossible to decouple those. So,
And I always think of traditional systems engineering as more like requirements definition and verification and things like that.
Diagram.
Yeah.
Oh yeah.
So we don't do that. I mean, we do that, but we do
That's
the
not
fun
all.
stuff too, where it's like, okay, if we're not hitting these requirements, like how does the vehicle need to change? Do we need to increase the size of the wing? Do we need to change the shape of the inlet to get some more performance back? Things like that.
Yeah. It's like we're the start of the iteration loop. Like we do the feedback, it feels like, through changing all kinds of things. One example of something I'm working on now is with one of the structures engineers pretty closely working on landing gear placement, and in order for us to do that, I have to feed him things so that he can make the CG move, and then everything moves, and then we get all our numbers, and it's like, oh, it needs to actually move more, and we're kind of that starting point. So.
I think that was one of the more interesting things, is like coming from more of a rocket background, how impactful landing gear is and how painful it is, because most of the time it's doing nothing. Right? It drives system configuration so hard, and unless you have a way to tie all those kind of pieces together that includes your center of gravity, includes your landing speeds, like the handling qualities, all of that feeds in and has a major structural like design configuration consideration. Like it's brutal. for how little you use it in flight.
Yeah.
Yeah.
It's a long process too to
it's
figure
brutal.
out when I was an intern in 2020, I started that landing gear loop, and I'm back full time in 2022,
It's like,
and I'm
Tatum, you gotta come
continuing
back.
it. Yeah.
Absolutely. So I guess, to that point, flight science has been around a long time. There were variants of it that, were part of the, Apollo programs. It's been around for as long as aviation has been around. I think it's having a new kind of resurgence with the way that the kind of new space has grown, as well as like the electric aircraft, VTOLs and things like that are taking off, and now high-speed flight as well. So what sort of things do you see us doing differently than a lot of other places, given that this is a very old, kind of traditional discipline?
I think one of the big things that we try to do is really stay out of analysis too much. Like we have to do the right amount, like make sure that we're answering the questions and getting to like a reasonable solution, but we can't continually like try to increase our fidelity on analysis without making sure that, we're making progress overall. Like we can get stuck in those loops really easily.
Yeah, that's super interesting because I think there's been, in the legacy Kelly Johnson days, everything was just design it on a piece of paper, just go lay it out by hand and just put it on there. And then modern computation came online, and it's great. It allows us to move faster and get a lot more fidelity. But at some point there took a turn to where it's like, there's almost too much of it. There's too much of reliance on it. And at some point, the amount of effort you're putting into increasing fidelity in your analysis isn't adding much performance, and it's adding enormous amounts of time to your programs.
I think the other thing is that we almost have gone back to that earlier phase where because we have a smaller team, you're required to own a lot more and understand a lot more. And so as opposed to like a big aerospace company, like I was in product development at Boeing for a couple of years and saw this where like you have the individual groups, like you'll have a mass group, you'll have a stability and control group, you'll have a aero performance group, you'll have a high speed aero, all of the specific things that happen are very separated. Whereas we, are forced to, because of our size, and also want to have everyone working on different aspects. And so you end up having a much smaller team that understands a lot more of the vehicle and then is driving the vehicle design from each person. Like James is working on the inlet and he's doing inlet performance, but he's also figuring out how it's going to integrate to the vehicle and the forebody, and so how that affects the overall the aerodynamics of the vehicle. And so that's something that other people at other companies would do, but it's really much more highly integrated here, and we want everybody to be driving that vehicle level change.
Yeah, you have to reach way beyond the interface.
Yeah, and to build off of that whole concept, I think Hermeus does a good job of all teams integrate well with each other, but especially flight sciences. I would say at other companies, flight sciences does the analysis, the very over the wall, whatever that saying is. But here it's so integrated, so I can go work with the GNC team and ask them, how are you guys thinking about the simulation, so I can make sure that I'm doing the simulation a different way, or I'm thinking about it the right way. And then across the company, we can make sure at a company level that everybody understands the vehicle better. It's nice to be able to be on the top level and see it all and figure out the distribution of it.
And I really want everyone on flight sciences to be a configuration engineer. And that's something that, takes learning and time. But as opposed to other companies where they have, a specific configurations group, and then they work with all the other subsets of flight sciences. It should really be that everyone is that configuration engineer as well, driving the change with their analysis.
Yeah, I think one thing we also do, especially probably in the last couple of months, we've really turned upped the iteration rate on configurations. It's absolutely crazy now how fast. I mean, it's basically we were doing multiple a day.
Yeah.
For a while, and now things are starting to stabilize. We just don't have to, but we have the ability to turn up that knob. I think that is a huge advantage because it's we're basically doing very, I guess, informal but very frequent design reviews, up to daily design reviews. And I think that just the understanding that you get from being able to see how your design affects the overall system, in a very small segment, how it affects the overall system and feed that back in nearly real time is an unfair advantage. Being able to do that is huge.
Yeah, I like the idea that it's a bunch of mini design reviews. I hadn't really thought about it like that because it's just such natural conversation now where we're just kind of in the mix and having these discussions. So, but yeah, that's
and
really,
it's not
really
hypothetical, because you're seeing like with these, model-based simulation tools that we've developed, you're bringing it all together. And so it's like the fidelity is still continuing to increase because we're adding better and better tools in, or, at some cases we can even reduce fidelity, but like have high fidelity models on like propulsion, but then have lesser fidelity. Like being able to bring those in a flexible way, I think really enables us to start to develop that intuition on the individual basis. And it seems like everyone's starting to get a really good understanding and be able to like see, like, to the story of Kelly Johnson, it's like he could see the aerodynamics, right? It's like we have to all get there, right?
Yeah, it's also one very big difference between more, standard or big aerospace companies is where they're looking at really similar configs a lot. And so like their tools are more standardized, especially if you're, working on airliners where you've been doing tube and wing forever. Whereas, we're trading pretty significantly different geometries when we're looking at this, and
people are gonna be super surprised by the new quarter horse.
Yeah,
I didn't mean to laugh.
So, and it's really just like limited by like what you can think of. We want to have that ability to radically change the geometry and not be beholden to some certain tools that we created to work with, this one specific like sort of quarter horse geometry, like the one that is sitting behind us.
Yeah. I think one other aspect that I'm pretty proud of the team for continuing to put out there is thinking of early design, especially as a cloud of possible vehicles rather than one specific kind of like point design. That's something that I had seen in a lot of companies where it's like, you go out to the aircraft design book and it says this is what you do for this, and then it's like a single point design that everyone designs to and they margin against, but you never understand how close you are to the design cliffs or like the Pareto front of possible vehicles. And so being able to incorporate uncertainties into our framework and like basically run Monte Carlos on all the kind of the space of possible vehicles around. Like if your engine performance comes in across this range, what does that do to the vehicle? When does that break down? What is the actual cliff of performance that is required for each individual subsystem? It's a pretty powerful tool that we have, and it seems like in most programs, at least I've seen, Monte Carlos only happen once the configuration's set. You're like basically significantly past CDR, and you're just like, oh, what can we do now with this configuration? And it's like, oh crap, well now we have to change the requirements.
Yeah, as this being really my first real job, it's weird to think that is, people have made planes and that was the way that they did it.
Yeah.
Because how I can't imagine us. I mean, obviously we have a tool that's very robust and built out, and it makes it easy to test a new configuration almost in real time. But it would be wild to think that you do this whole design and analysis and then you get somewhere and you're like, oh gosh, we're not going to hit our target. And then you have to, wow.
It happens.
It certainly happens.
But I think also it's like we talk a lot about bringing new space to aviation, and you see that big difference in bringing Monte Carlos in earlier, things like that, in new space companies for sure. And so I think it's another kind of area where we're bringing in a lot of that like newer technology, newer thinking into aviation, as opposed to in some ways we have the benefit of not having tools that are built from 40-year-old, 50-year-old, things, which enable you to do very like quick design because there's been a lot of history behind it, but they're probably not as agile.
Actually,
definitely not as agile.
All of this made me realize that some of our audience might not know what a Monte Carlo is. So, what the hell is a Monte Carlo? Someone want to take that?
Sure, I'll take it. Yeah. I like how every face in succession just turned. I forget what they're exactly named for, but
probably a guy named Monte Carlo.
Yeah,
but
that tracks.
It's basically when you have a bunch of uncertainties, and then so you have this like parameter space that you could pull from, and when you have a variable that can change like on drag or lift, but that they're not necessarily all going to be like the worst possible case or the best possible case at all times. So you want to basically randomly select somewhere between best and worst across all these different variables, and then you run just a lot of simulations. And over time, you start to be able to pick out like the boundaries of what the performance will be. There will be like some certain cases where, you know, you get a lot of like really terrible draws that give you bad performance, and you'll get some that are like really great performance because you have like super low drag, really high thrust. And then the way that we look at them is we know that, you know, some certain percentage of those like are not really going to be actualizable, right? Like you're not going to get your absolutely worst drag, your absolute worst thrust, your absolute lowest lift. And so, you know, you have some, it's possible, but it's like a point, it's like a long tail.
Well, yeah, it's an uncertainty distribution that you're applying to parameters that you are uncertain about, right?
Yeah.
And I think it's, you know, being able to have that in the tool very, very early when we are closing that iteration loop is what helps develop the intuition. You can see like what things have strong performance partials on your vehicle, and so it's really cool. And that is one thing where it is only enabled by our ability to simulate. Like that is something where it's like we are leaning on very heavily, and it's relatively modern. I don't know. I mean, it's been around since computation at this point, but like, you know, being able to do that is something that they didn't have in the 60s and 70s, and which is why we can get to deeper and deeper into the corner of the like physical envelope.
Yeah.
But yeah.
And even the concept of the Monte Carlo as we continue in time gets a lot more robust and capable. It's not as simple as just the statistical uncertainties that you used originally. It's now getting even more robust in the fact that we're able to fold that into our tools as the statistical analysis becomes more intense is quite useful.
And to your point about, you know, figuring out where the steps are, it can really help you figure that out as well, because if you see, oh, we're failing at transonic a lot because when we get a bad draw on drag, you know, transonic is a place where lots of airplanes have issues. That will let you, you know, understand what's driving that specific like step change and be able to go in and fix it somehow.
Yeah, I mean, and that's how you can actually create an informed requirement. Like these blanket, you know, margins of like, oh, add 20% margin to all your mass parameters. It's like, what is 20%? Like, what is that? Yeah. Who even knows? So being able to have an intelligent margining strategy is like an enabling feature, and it's pretty cool.
I mean, similarly for loads, which we haven't really talked about, but that's a big part of flight sciences as well. And it's like, well, you could create, you know, your VN diagram and like just design to those points. And, you know, it's helps out a lot with early design to only do a couple cases sometimes. But in reality, you're going to be flying like a bunch of different mission profiles. And so running a flight sim with a bunch of Monte Carlos where you can see what the actual load distribution is, you can, for a vehicle where, you know, every bit of mass is important, like that's a big deal, as opposed to just like designing to these corner cases. It's like, okay, what missions or mission profiles are we actually going to be flying, and then trying to design to that instead.
And to your point about rolling in uncertainties or like rolling in new information, so like reducing those uncertainties over time and then updating the kind of baseline values, like how critical was it that we were testing the engine to see that the like as advertised performance of the JD5 is like nowhere close. I mean, it's like it makes sense that it's not the same because anything coming off the assembly line is obviously going to be better, especially for an engine that is as old as the J85. But like, whoa, what a dog compared. And it's like, but if we hadn't tested and then hadn't rolled all of that back in to, you know, our flight sciences analysis tool, like, holy shit, we'd have been in a tough place.
I mean, we'd still be working on that.
Yeah, that's why it's a different airplane. Yeah. About the same. Mostly the same.
Pretty close.
Y'all,
this is light tweaks.
The audience will see soon.
Yeah.
Spoilers.
The second quarter horse and fail.
Cool. So I guess, you know, this is kind of like the last analysis step where everything kind of comes together. You know, what other simulation techniques, what other analysis techniques are you all using along the way to help create the inputs to this, you know, final step?
I feel like this is a James question because James loves simulations and tools.
I do love tools. Yeah, I mean, we run a lot of CFD, at least on the aero side, just to be able to try and quantify what sort of performance we can expect from like lift and drag perspective at the external aero level, but also then like factoring in like what sort of flow field distortion do we get for an inlet? What sort of pressure recoveries are we getting through our system?
Mm-hmm.
And those kinds of things all add up, and those are great. But then like outside of that, we've developed a pretty sweet tool chain to be able to go through and like iterate through those performance parameters, like we've said with the Monte Carlos,
Mm-hmm.
and we call that like our vehicle closure tool,
Mm-hmm.
and that is where like the magic happens, I would say,
Right.
where it is like we're rolling everything together. We're seeing how all of these different systems are integrating to like the final vehicle. And so like those things have been some pretty powerful tools for us. We do a lot on the prop side as well to try and model a full cycle for this engine and integrate our hardware in to be able to do all these fun things. But
Ferrari's going now.
Yeah, we got
all
right.
right.
What sort of things, I guess, with the CFD and the simulations that you run, what keeps you up at night? Where are the hard parts?
Shock boundary layer interaction.
Ah, yeah.
Oh man, gotta figure out those bleeds.
Uh-huh.
So yeah, for
Certainly.
me, it's looking at those like initial analysis with the viscous CFD turned on, and it's just like, all right, well, I'm seeing some really crazy results here.
Mhm.
Is this something that I can actually control with a bleed? Is
Right.
this something that like I need to really refine on? And that's where I start to go into that mentality of like, oh man, I can dive down this rabbit hole of looking at this one thing really in depth, or I can probably do some wind tunnel testing on it and learn a lot more.
Mhm.
Or look at something that other people have done and see like, hey, how did you guys handle this?
Right.
So
Cool. What keeps you up at night, Tatum?
How to optimize the tool and mass of the vehicle for sure keeps me up at night. Tracking it, making sure that when a team comes to me and tells me, hey, my system's going to go up by 300 pounds, how I'm going to break that to Danielle. That's what I
It's all
think.
storytelling. Yeah.
Yeah. And just when we were talking earlier about how flight sciences really communicates between teams, it's very useful to be able to, somebody gives me a mass and I'm able to be like, okay, well, actually, I know that this person's tracking that in a different way, and you definitely need to talk to them to make sure that so that our tool works, all of those systems are being tracked like that.
Yeah, there's an enormous amount of assumptions that go into the estimates that everyone has for mass, right?
Oh, yeah.
Right?
Yeah.
And creating a consistent approach and a consistent margining strategy. Like, engineers love to succeed. So it's like, I mean, I can say this because I am an engineer, but it's like, so you always hold a little pocket margin, but then the stack up of all that pocket margin is just like, well, now this vehicle doesn't work. So it's like, what are we going to do now?
Yeah, and you were talking earlier about those random numbers. It's like, 20% margin, there you go. We can roll that in, but with our uncertainties, we are able to pick a random, point in that range, which is nice, I'd say. But yeah, it would definitely be mass of the vehicle that keeps me up at night, without a doubt.
Probably all the veteran aerospace designers are like, yeah. I don't know if there's ever been an aerospace vehicle that wasn't like, hey, let's dive a little deeper on the mass here.
Yeah, and also expand. But instead of just tracking it, I am trying to create equations so that we can predict it better for our next generations of vehicle.
Yeah, that's a super hard problem, right? Is like
you're telling me.
Well, I mean, for people who don't know, right? Is being able to predict these vehicles that there's not like an empirical database of all these different hypersonic vehicles that we can just say like, oh, well, something that goes this fast and is about this size, it's gonna weigh like this. It's like there are some tools that come out of papers that you can do, and they're all bad.
We tried it and they don't work.
Yeah.
So
yeah, working off of that though is quite tedious.
Anything for you, Wes?
I mean,
what doesn't keep you up
Yeah,
at night?
I was
Wes?
about to say.
Yeah, I think it's probably more like the unknowns right now, or things like where we know we need to add more fidelity, and we're just, making what we think are conservative assumptions right now, and then, like for instance, like building up to the flight sim. We're adding functionality to that as we go. And we've tried to account for all of the, like the difference in fidelity by adding some conservatism. But you don't truly know until you really add all that fidelity in. So I think that's like the thing that is most concerning to me.
Certainly. So I guess as a little segue here, we talked about simulation. We talked about all the kind of difficulties of simulation. So how do you know when to stop analyzing?
Broadly, when you're holding back your other teams.
Right.
July 11th. Yeah, I mean, I think part of it is like what we've been talking about with the Monte Carlos, right? Like, for us, this vehicle has a very specific requirement. It's hit hypersonic and be reusable, and we want to do that with enough certainty that we believe this vehicle is capable of it. And so it's a little bit of a...
I think even beyond that, to put an even finer point on what it needs to do is like, we really have to fly a TBCC, right? That's the thing that unlocks a new world is like, I guess the SR, like the J58 from the SR71 is a very similar architecture, but not technically a true TBCC, right? So being able to fly that is now a capability that no country in the world has, right? So sorry to derail that a little bit, but like it's not just, let's hit this number. It's more important about like, now our engine is at a flight proven TRL and this architecture is real and we're not just a bunch of people who are full of shit.
Yeah. So like as soon as we believe that we can do that, it's like, go. Now, obviously, like, so instead of like needling on some performance thing, like, we could reduce fuel burn by this much so we can increase our payload or our range. It's, maybe we could increase the probability of success a little bit. And that's a really hard question, but I think, at a certain point, it's really like trusting in our tools and believing that, we understand, the probability of success and sticking with that and moving forward.
Any other thoughts there?
Nah, that's pretty good.
Yeah, no, I think it nailed it.
Yeah. I think it's when the right time is like when just going and testing it reduces so much. Like there's just so much uncertainty of just like there it is and it's doing the thing, right? We know exactly how much fuel burn. Like your uncertainty band gets very, very narrow when it's running.
Yeah. It is an interesting question though, because like I think about how much we've learned in the last 3 or so years. Like I look back at some of those OMLs at first year. What the hell was I thinking? But like we learned a lot from all of that design work and that iteration. And so like there's definitely that part of me, and I think a lot of engineers, it's like, okay, but like the next iteration will be even better because we'll learn some more. And so I think we really have to like be cognizant of like the overall company picture and like the vehicle picture and not get stuck in that loop, which is exactly what you're talking about.
Right.
And so like knowing when it's time to pull that plug is really tough.
There is some sort of like analytical gravity around like when it's not working and you're like, I think I can get it here. Like you feel like it's there and you're like, if I could just tweak this, it's going to get to this level. There is some sort of pull that I've felt where I have to like intentionally stop myself and just be like, yeah, but actually who cares?
Yeah.
Right.
Let's go build it and let's go actually see. And then it's also way cooler when you actually build stuff.
This isn't even flight sciences related necessarily, but like I think over the last year, just learned how important it is for these like milestones that we set ourselves. Like, because there's like the Hofstadter's law, which is like everything will take longer than you expect, even when you include Hofstadter's law, or like, things always expand to the amount of time you give them. So there's also, I think, I've learned that there's just a lot of value in, like setting a date and hitting that date. And that's when your analysis is done.
Right. Yeah, certainly. So you mentioned a little bit about developing an intuition around, OMLs and probably anything that we're designing, right? So I guess this is now going to start to get a little more philosophical, but like, what role do you see for like true computer-driven optimization for hypersonics and like how we develop computer intuition around these things? Is it possible? Is it around the corner? Are we going to build it in the next couple of years? Where are we at in that, and how do you guys see that?
Well, Tatum's been reading
yeah.
about this like
Ah.
5 minutes before we hopped on this
Yeah,
call.
we had a
so
couch chat earlier today. That is what we're going to do. Like, and by I'm putting it into the universe. It's happening.
Ah.
I'm making it happen.
Okay.
You're
Damn
manifesting
it!
it.
Yeah,
I'm
100%.
manifesting
Yeah.
the
Machine
like
learning.
deep algorithm. But yeah, we without a doubt will be able to. Well, maybe not without a doubt, but a little bit of doubt at the beginning. But we'll be able to do it. There's no way for the level of, I wouldn't say experimental technology, but like you were saying with the mass things, it's like there's supersonic vehicles that I can pull numbers from and get a nice little curve to see where should our mass lie. But the performance of those vehicles is so much different. So we are going to need to do machine learning to really have fidelity in our iterations, kind of thing. Enough fidelity to iterate, I should say.
And at the risk of like expounding on something that I'm not an expert in, there's a wide range of like what machine learning is, right? And so like at the basic level, like we're already starting to do it with optimization, and we're building more and more of that into our tool chain with optimization, multidisciplinary optimization tool chains, things like when we're running CFD, like figuring out intelligently where to add more fidelity in the CFD analysis. Like where do you spend more money to do viscous runs versus doing inviscid runs? And those things are all like on the lower end of like what people would consider machine learning, but it's like it really is like taking in data and learning and understanding. The higher levels are going to be pretty fun.
And to fill in the philosophical kind of idea on the higher levels, being able to, like, your algorithm's only as smart as your programmer, and so if we are able to if we're able to teach our machine how to do things from many different angles, make sure that the robustness of making this algorithm is coming from many different people at the company and they can understand it, then all of a sudden, now we have a tool that learns very well. We created a brain. We're creating a new human. Yeah, no.
I also think like the intersection of flight sciences and GNC, which, you know,
that's a big overlap.
Yeah, there's if the Venn diagram, and a lot of companies, you know, like GNC is in flight sciences. I think that's like a big area too, where it's like learning how to fly the vehicle. You see it with driverless cars, things like that. You know, like that's a huge area of emphasis for machine learning AI. Figuring out the same thing for our vehicles, like how they want to fly, what the like aerodynamics that are going into them. Like as we create more data, we have to figure out like what truth is.
Well,
that's the philosophical question.
So actually, I don't know if it might be surprising because like I am very much like an optimist by nature, but like I'm actually near term very pessimistic about AI ML for this type of thing. And it really comes down to the training set. I just don't think, like, especially in hypersonics, we don't have a training set that's anywhere close to being able to do it. And so what ends up happening is if you apply it too early, you're applying it based on fragile dynamics and you're actually over optimizing into a space where you don't really have the data to support. So it's like, I actually am anti optimization until the right time, even not talking machine learning AI, but like even just an optimization. Because like if you embed, if the algorithms that underlie your optimization are different from reality, which they certainly are, but far enough differently, you can optimize into a corner of a numerical space that is not physical at all. Right? Yeah. So it's like until we have a rigorous, large enough data set, that's when I think we can unlock different things. And so I've seen some interesting things where it's like, have you seen the 2-minute papers thing on YouTube? It's like an AI focused, like, have you seen it?
Is it the one where they're just like writing based on like what they have programmed as like a data set? Like what sort of thing?
I'm not sure exactly, but it's like, I think he like the author or the video producer like goes and finds a paper and then like shows a visualization of what's happening within the paper, or like shows the visualization that they created themselves. But there was one where it was just like taking like Google Earth physical real world images and then applying it on top of like Grand Theft Auto data and make it hyper realistic, right? That's super interesting, but only because there's this like giant, enormous data set. So there's an implication where it's like, well, if we get to the point where we can adequately predict using machine learning like CFD or aerodynamics, especially complicated ones, we could run it in the loop really fast. And if you're running CFD in the loop, pseudo CFD, but like machine learning CFD in the loop, that unlocks a whole new world because you can do it on the fly, you can simulate on the fly, and you could enter new spaces just as you enter them. Like you wouldn't have to do it on the ground, you could do it in situ, which is crazy.
But would you be able to incorporate, you had mentioned earlier when you incorporate, how do I even word this? You had mentioned earlier, how do we iterate such that you get 80% of the way, and then but you still have space, so you're not just trying to get that perfect number. What's the difference between that and this machine learning? You say like, okay, well, if it's actually machine learning, like we have to do some amount of human learning before machine learning, or couldn't we just fold that human learning into your machine so it's learning with you?
Yeah, I think certainly that. I think in my mind, it just comes down to the data set. Like with a big enough data set, you can construct a model of reality that is accurate, but and even beyond what we could even see. Like you could find corner cases, assuming that your model reflects reality good enough. And I think that's what comes down to, like, that's the underlying assumption with any simulation is like, does that simulation adequately reflect the dynamics of the system you're trying to predict and optimize?
Yeah, and when I said, you're trying to understand what truth is, I mean, like, when you have, like, a 6DOF database, so, like, your XYZ forces and moments on the vehicle, we have CFD that gives us that as a result. That's one input. We have, like, wind tunnel tests we'll be able to back that out. We'll have flight tests that will give us some of that data. But all of that data has, certain errors or biases. Like you're not perfectly modeling things in CFD. In the wind tunnel, you have sting effects, wall effects, the Reynolds number effects because you're not full size. And when you're flying the vehicle in flight test, you have like the atmosphere is going to be different from day to day, from as you change in altitude from what you might expect. You'll have crosswinds. Your mass will be different.
Right.
All these uncertainties, and you have to figure out how to like combine them in a way and like figure out what you actually think truth is, or like what your nominal is. And I think that's like a very like strong case, and because you don't want to go into flight test and you have your first flight and you're like, oh well, this line is like kind of off this line that we had from CFD and wind tunnel tests, and you don't want to be like, okay, yeah, I'm going to change it to flight test right away because that would be bad because you're just dropping out all this data that you have. So figuring out, like how do you want to start adjusting the plant, like all the forces and moments that go into the flight sim. And the flight algorithms as you add more and more data. I think that's a really great place that you can add a lot more knowledge and like
Intuition.
And
Yeah, it's pretty fun. So, but prove me wrong. Make it.
I will.
1 year.
Okay.
Hell yeah. All right, cool. Have you guys, speaking of all the AI ML stuff, have you guys been following the DAL-E saga, which is like you type in a thing and it generates images via AI?
Oh,
have you been following this?
Yeah,
you gotta go on Twitter. It's amazing. So it's just like Shrek in a courtroom, and then it's like courtroom sketch of Shrek, and it's so funny. They're so good. But like that's the optimistic side of me is just like we'll get there when the data set's big enough. So that's pretty fun.
Yeah, I mean, I have played around a bit with like the Google freely available stuff, and the amount of capability it has is quite crazy. Like that's already open source and out there.
Oh, and then there's Lambda, right? That's the other one that just came out, which is like simulating a conversation, we'll say. I think that's I don't know.
Is that the one that Google's working on?
Well, I mean, one guy thought it was like the guy from Google thought it was sentient, and like, I mean, it opens a broader question. Just for the record, our aircraft is very far from sentience. We don't have to worry about our aircraft's rights. We're very far from that. Yeah. But no, it's interesting questions, and it's like, at some point, I guess our aircraft could be there, but that's really far out stuff.
Will be there.
I'm gonna have to go.
I mean, do we want it to be? I kind of like our aircraft not being sentient.
I don't know. It's like riding a horse. You can like you can teach it where you want it to go. You just have to ask instead of give it a mission path
Right.
now.
I mean, I think the mission side is like a really cool place to investigate this whole idea, right? Like, if you could have multiple Darkhorses or more than two, like a fleet of them, like what is the best way to have the swarm do ISR things like that?
Oh, that's super
Yeah.
interesting stuff. Yeah.
Yeah, that's the level that you would want it to be, is just so that they could communicate.
Coordination.
Yeah.
Certainly.
Do like a synchronized swimming routine.
That'd
at
be
some
beautiful.
point.
I mean, that would be pretty awesome. So it's like the scene in Top Gun where, the aircraft buzzes the ground and like blows the roof off the building in the new one. But just have like a fleet of those blowing off lots of roofs. That'd be sick. What'd you guys think of the Top Gun? Have you seen it?
No,
You haven't seen it?
I'm seeing
None
it
of us have seen
tomorrow.
it.
None of you have seen it?
Wow.
I'm seeing it tomorrow.
Cut the podcast. This is
Oh, no.
it's ruined. How can you guys call yourselves
We-
aerospace engineers? What are you doing?
We're out here building brains.
Oh, that's
Making
good.
real shit?
I'm an executive, so I don't do anything
Oh,
anymore.
gotcha. Yeah.
I just hang out and philosophize about artificial intelligence. I don't
Watch Top Gun.
Yeah, exactly. I will say though that like for it's kind of corny. I mean, like everyone knows, but it's like I did feel some things. I'm like, we got to build this airplane quick because it's sick. Yeah, it's cool. Any other things you're thinking about? What are you guys working on outside of Flight Sci? Do you have any fun side projects that you're working on?
Well, I have my second job, which is head of Darkhorse.
Yeah.
But that's a ton of fun, right? Because it's like looking at all of the requirements. Like we have a capability for a vehicle that can fly longer distances.
Yeah.
And what do we even want to do with that vehicle? Like, what are the capabilities that our customers want? So it's really interesting because it's really trying to develop a lot of those requirements, figure out what the con-ops that we want to fly are. So that it's in a really interesting phase of development right now.
Yeah. It's super fun too because there are a lot of things that get better with scale.
Yeah.
And having a bigger vehicle with other features, I guess we don't want to go into too much. We got to keep a little mystery around that vehicle, but like it's gonna be awesome.
But turns out a J85, which is like a 60-year-old jet engine with a really low compressor ratio, makes it for a tough vehicle. And more modern turbojets, turbofans, things like that can give you a lot of performance back that we're not working as hard with on quarter horse to get through some of those pinch points.
Yeah.
I think the thing that we haven't really dealt with yet on Flight Sciences has really been getting some of our stuff into testing. So like a lot of the wind tunnel test planing and things that are coming up, like that gets me really excited. That's the stuff that I'm like, this is where I get to spend some extra time, do some work that, gets me interested in like validating my models and just like, I want to get there.
That's something we didn't talk about at all, and Jonathan's gonna be so mad. And like, obviously, it's like, why didn't we talk about that at all? It's like a major design consideration that we're constantly like stressing about. Like, that's so funny.
Yeah, we didn't talk about how hot things get.
Yeah,
to be fair, Jonathan said he didn't want to be on the podcast. So,
but we just talked about him and like, yeah. There's lots of problems there, man. Yeah. Maybe for a different podcast. Like we could probably do a whole
The thermal podcast.
Yeah, we could probably do a whole one on that.
Yeah, just hot boys.
Yeah,
Hot boys.
Just do hot ones.
Yeah, there we go. Just do hot ones.
Do hot ones.
That'd be great.
Make him
Make him
that'd be
eat
great.
the wings.
And Federico's starting on Tuesday.
Oh, yeah.
So
yeah, there we go.
Wait, that could be really
Welcome
fun.
to the company. Here are some extremely spicy hot
We
wings.
might not be able
Yeah.
to call it hot ones, like hot things
that's
or
true.
hot units. That's maybe not that.
No, Vita.
All right, cool. Any other final thoughts for people thinking about, getting into aerospace or getting into, this area?
I mean, I think for like flight sciences,
Like students, yeah.
yeah, like.
Do you
being
recommend
able
flight
to-
sciences?
Oh yeah, absolutely. And I think like first principles goes a long way. Like you can run CFD and still not be a great flight sciences engineer because you don't have the intuition for what your
Right.
CFD should be doing.
Right.
So like develop that understanding if that's something you want to get into.
Yeah.
I think you really need to know how vehicles work or how airplanes specifically work. And so doing something like a DBF competition or similar, where you have to go through a bunch of iterations where you're actually designing airplanes and seeing how all the systems, fit together, how the aerodynamics affects or, like stability, where you want to place your wing, things like that. I think that's like very invaluable experience that you can't really get just through capstone courses and
Right.
things like that.
Well, you really have to close the loop. You have
Yeah.
to get through a full life cycle to
Mhm.
actually say that, like, I mean, like those early conceptual design tools or papers or algorithms, it's like, well, this is trash because the loop never got closed because we haven't flown vehicles like this.
Yeah, and there's nothing worse than an analyst that has like never really worked with hardware.
Yeah.
You know,
Right.
I'm sure structures would still laugh at me for saying that.
But
But
you don't even know hardware.
Yeah, you don't know. But like, really, like you need to really understand the like how the systems work together and have some experience with the hardware yourself in order to do a great job.
Yeah.
There.
Or else your analytical teams end up doing that, kind of that cartoon that's always, it's like aerodynamics and it's like a very
Yeah,
sleek plane.
yeah.
And then it's like the structures team and it's a bunch of I-beams.
Yeah.
Yeah.
It doesn't
It
have to be
becomes that.
doesn't have to be anything crazy easy
Yeah.
either. Like when Tatum was an intern, she was working on
Avionics?
various things, but avionics bay
Yeah.
among others, which
No, I
is-
mean,
is
I
still a
was
thing.
on avionics. Like, I wasn't on the
No.
flight sciences team, and I'd definitely say that the flight sciences, you hit the ground running a lot faster because you do have to understand the config and also, I guess, the nature of the job. I was an intern learning.
Yeah,
Mhm.
but it really, I think, like helped you understand a different aspect, and like you got your hands on with, some of that avionics. Like,
Oh, yeah.
you're doing like PCBs and things like that.
Yeah, but I was lucky enough that the company was so small when I interned that I was able pretty easily to work with.
You did a lot of stuff.
Yeah.
Well,
I
you
re-
got us our first start cart.
I did.
Oh,
Oh,
let's
yeah.
go.
I
Have
remember.
you started that yet?
No.
Wait, you
You
haven't
still
even
need to
pushed the
run it.
button? Oh, you
No,
gotta
I haven't
run it.
even pushed the button. No, but
Oh, man.
I remember when I was on the avionics team, it was so small, and I referred to us in one of our stand-ups as the avionics team, and you and Anthony were like, "Oh my gosh, we're a team now!" Like,
Aw, yeah.
so it was
Was
easy.
it the three of you?
Yeah. Yeah.
Nice.
So it was easier to I remember talking to one of the other interns that was leaving, in our stand-up, because we used to have a big stand-up where everybody would participate, and basically poaching his project off of him. I was like, "You're leaving. I'd like to take this over. Thank you."
Jacob.
Oh, yeah.
Jacob, yeah, that was the one. And then the Avi Bay cooling initial
Oh, yeah.
cycle was born. But yeah.
Man, that's great. I'm so glad there's an avionics voice in flight sciences holding it down for us.
Mm-hmm.
Underserved.
Yeah, we never
Underserved.
talked about how you got your honorary flight sciences
Oh, yeah.
moniker, but you wrote your baby is the closure tool.
That's
like,
right.
The little like kernel, more than the kernel, like a lot of the initial functionality of it was you. And so
I mean, man. Yeah. It's hard for me to step away. And like Tatum came in and like was asking me questions about like how to train people up on it. I'm like, don't get involved. Don't get involved. But it's like, oh man, there's pieces of that where it's just like we were talking about it, and it's just like some of the low level code, like some of the interpolation functions and like the file handling stuff. I'm just like, if anyone touches that, I'll kill them.
Yeah.
It turns
Like-
out when like someone with a software background is writing this stuff, it's way better in a lot of ways.
It works out. Nice.
Yeah,
Oh, yeah.
I started, most of my background was more like engineer tools that hadn't been written from someone with a software background, and I started Hermeus, and I'm like, oh shit, I gotta learn object-oriented.
I know that was one of the
way
first
better.
thing I was like, all right, we're gonna get you on Git. We're gonna be committing.
Yeah. Oh man, these classes and stuff. Yeah.
Yeah.
Oh yeah, it's beautiful though. It makes way more sense.
Yeah, it does.
Yeah, and I wouldn't even call myself a software person. Like
Yeah.
I'm a kind of honorary a lot of different things. I'm like honorary avionics, honorary software, honorary flight sciences.
Mhm.
It's important.
yeah.
Founder.
It's all important. I don't
We'll
know.
claim you.
Yeah. Hell yeah. Awesome.
Nice.
Cool.
Yeah.